but you actually were working with these in lab yesterday when you're doing the titration of the weak acid. You were using a buffer system. And that's really the main subject, one of the two main subjects that we're going to focus on in Chapter 16. So buffers, they keep solutions at approximately the same pH, even though you've added acid or base to the solution. And this happens due to Le Chatelier's principle, which you already know about. It's where you have a weak acid or base. Weak acids and bases form buffered solutions because they are in equilibrium. And Le Chatelier's principle, you know as the equilibrium will shift to adjust due to some stress put on that system to form a new equilibrium. Now in this case, the equilibrium is going to involve hydrogen ions, which translates into the pH of the system. So you're going to see now Le Chatelier's principle in action as we add acids or bases to a buffer system, and we'll be able to see as these equilibria shift to the left and right, the hydrogen ion concentration here in the middle isn't going to change that much. And in fact, this is a main one right here that keeps you alive right now as you're listening to me. Even if you're falling asleep right now listening to me, you're still alive because of this reaction. This reaction happens in your blood, okay? Blood pH needs to be at 7.4 plus or minus a little bit. If you're out of this range, if you go beyond 0.05 pH units, either above or below, you're in the hospital with either acidosis or alkalosis. I'll let you decide which direction the pH goes to have which clinical syndrome. All right, but the symptoms are kind of like you're delirious, you're kind of sleepy, kind of like how you are after one of my lectures. All right, don't quit my day job, right? It's pretty serious. It's a pretty serious condition, but it doesn't take much to get your blood pH to be out of this really, really tight range. Now, what do you suppose happens if you get beyond that range? You're dead. That's right. No joke. You're dead. Now, when you go on and take biochemistry, you'll understand a little bit more about why this is the case. But all your proteins and enzymes that keep you alive, and especially the ones that are in your blood, they fold the way they do in three-dimensional space. A lot of that is determined by the local pH environment, because your amino acids, some of them are charged, some of them are not charged. That influences how they fold in 3D space. That's totally affected by the pH. So if you change the pH, you're changing the charges, right? The hydrogen ions in there. That's going to affect the charges on the amino acids. That's going to affect how the proteins fold. So yeah, you're very, very quickly dead. But thank goodness for you, we have something called carbonic acid. That's a weak acid that sets up the buffer system in your blood. Here it is. Can you tell I like talking about this subject? So here's carbonic acid. We've looked at it. It's one of your weak acids. We could describe the Ka for it. Right? We're not going to do that now. On the right-hand side, here's a reversible reaction that you're quite familiar with. Right? It's weak to produce hydrogen ion, and what's this thing called here on the right? The bicarbonate ion. Now it turns out that we can also make carbonic acid simply by merging carbon dioxide and H2O. That is a reaction. It's actually influenced by an enzyme called carbonic anhydrase, but this isn't a biochemistry class, so I'm not going to write that one down for you. Okay? But we breathe in carbon dioxide, we breathe in liquid water, all right? But mostly the carbon dioxide, we breathe that in. That gets absorbed in the tissues that line the lungs, right? The barrier between the outside and inside of your body. So that carbon dioxide gets into the blood, mixes with H2O. We have enzymes that convert that into carbonic acid. And once that's made, because that's a weak acid, it dissociates H plus and bicarbonate ions. Now, obviously, this dictates what the pH of the solution is. Actually, we're in the blood now, so I should really write this in red. Okay, so here, now we're in the blood. Now, the same reactions happen when you get to the tissues. In the tissues, we can get this turning back into carbonic acid by the same enzyme, by the way. And then carbonic acid can dissociate back into carbon dioxide and water. Now, I know you guys haven't taken biochemistry yet, but when you start studying the metabolism of glucose, C6H12O6, and you mix that with O2, right? This is cellular respiration. What are the products of cellular respiration? CO2 plus H2O. Well, here they are. Okay? So your cells, right, just by making energy, produce carbon dioxide, right? That's one of the byproducts of cellular respiration. So that gets back in the blood, and it gets carried back, and you finally exhale it. But look at this. Carbon dioxide doesn't appear anywhere in here. This is actually how you transport carbon dioxide from your cells into your lungs so you can exhale it as a byproduct of metabolism. Fascinating, isn't it? But what's also fascinating is if you start to throw your blood pH off a little bit, say, I don't know, maybe you breathe too heavily. What happens if you breathe too heavily? You hyperventilate. Has anyone hyperventilated recently? Like before one of my exams? Oh boy, I just keep them coming. All right? You hyperventilate, right? You're breathing all this in. You're breathing in all this CO2. So by Le Chatelier's principle, what's happening? You're increasing this because you're increasing this. So it shifts to the right. This increases, which means it shifts to the right. And look what happens. Your hydrogen ion increases, so the blood pH goes down. You're getting more acidic. You're about to suffer from acidosis. And if you do it too long, you're going to be dead. So you regulate your breathing a little bit. Maybe you slow it down, right? Now you're lessening this carbon dioxide over here. The reaction shifts this way. This shifts this way, and the blood pH starts to go back up again into our safety zone. And that's an extreme example, all right? But buffer systems like this work because of Le Chatelier's principle. We can adjust this equilibrium to the left or to the right as we need to maintain a very, very tight pH in the blood. When you make a buffer system in the laboratory to do an experiment, it's the exact same thing. You use a weak acid or a weak base to make a system that's then resistant to large fluctuations in pH when you start adding acids or bases to it. Right, so that's kind of my intro into what a buffer system is and why they're important. From a biological standpoint, of course, we're doing it for chemistry. I won't go through this last example. If this were an environmental sciences class, I'd talk more about this reaction and how it's, never mind, I don't want to get into it. It's fascinating, but we're not gonna get in there. Instead, let's transition into the common ion effect, which also can influence how these buffer systems shift left and right. Adjust. It's all the Chatelier's principle. All the common ion effect is, I'll just say, it's all Le Chatelier's principle. Let's spell it right. Just put a little hat on there. That's how you spell it. And we all know what Le Chatelier's principle is. So here's a case. Let's say you're going to take some Alka-Seltzer. Anyone taken Alka-Seltzer before? When you have an upset stomach? Your stomach's upset because you have too much gastric acid in there. The pH is getting too low. Right? And you get acid reflux and all that nasty stuff. So you take Alka-Seltzer. Alka-Seltzer is sodium bicarbonate. sodium bicarbonate, is that a strong or a weak electrolyte? You remember how to evaluate that? The solubility guidelines, any group 1 cation will be soluble under general laboratory conditions. So anything with sodium should dissociate 100%. Whether it's 100% or not doesn't matter. For this discussion, it dissociates into sodium ions and bicarbonate ions. Now here's our friend carbonic acid again. So I've got an upset stomach, so I'm going to eat some Alka-Seltzer. All right, that's going to give me bicarbonate ion in my stomach, and my stomach is upset because I already have really, really high levels of hydrogen ion in there, too much gastric acid in there. Well, these are two components of a buffer system, right? Because you mix them together and you get carbonic acid, which is a weak acid. So these are in equilibrium. So if I take some sodium bicarbonate, I'm increasing this, so I'm increasing this. Before we increase this in blue, though, we have an equilibrium set up here. All right. Well, we don't have any bicarbonate yet. We haven't eaten any yet, so we just have high H+. But now we're introducing lots of bicarbonate ion in there. That's going to merge with the hydrogen ion, and overall we're going to get a shift in this direction because we're going to combine them and push the reaction in reverse. That's going to end up lowering the pH, raising the pH, right? We're taking away the hydrogen ion. So this will end up raising the pH. And we're doing this by adding a common ion. What's common? The bicarbonate ion. Right? We're basically adding a component of the buffer system to push it one way or the other. That's essentially what the common ion effect is. In fact, there's not really much more for me to say about it, but know what it is and know what to do with it when you see it. And actually, I'll just remind you, this is no different from earlier in the equilibrium chapter when we were evaluating Q versus K and trying to figure out which way the reaction is going to move. Okay, so with a buffer system then, we can describe how things will change and describe the pH. And all we're going to do is take our friend, the equilibrium expression. So here's our weak acid equation. Here's the Ka in the mass action expression that describes the Ka. All right? And we're going to do a negative log transformation. We're going to take the negative log of both sides. And when we do that, we're going to have the negative log of the Ka is equal to the negative log of H plus concentration times A minus concentration divided by HA concentration. But I wrote it this way so that I can separate that out into minus the log of H plus the negative log of A minus divided by HA. That's just how logs work. It's one of the identities of logs. Again, in case you're wondering, the magic there, that's just the log of AB is equal to the log of A plus the log of B. That's all I did there. I'm now going to remind you that this term here, this is the pH, negative log of H plus. So we're going to call this the pKa, negative log of the Ka. And then I'm just going to rearrange this equation so that we can solve in terms of pH. The pH is going to be equal to the pKa. I'm basically just going to take this term and move it to the other side. So that changes the sign into plus the log of A minus concentration divided by HA. Okay, so now you've seen this derivation twice. It's not a difficult derivation. And it's one way to help you remember what the Henderson-Hasselbalch equation looks like. I'll give it to you on the exam, okay, for you to use. But you might not always have me for a class where you have this equation, but it's super easy to derive. All you have to remember is the mass-action expression, and then just do a little bit of algebra and logarithmic stuff, and you're there, okay? But now we're going to explore what this reaction actually means and how to use it and how it relates to what I just talked about with the buffer system and the common ion effect and all that jazz. Now, this also will explain what's bulleted up here at the top, but I didn't talk about. A buffer system, right? I told you earlier, the definition is that it resists changes in pH, strong changes in pH, when you add a little bit of acid or base to them. But I'm going to add on to that now. They're most effective when you're within plus or minus 1 pH unit of the pH that you want to keep things at. Okay? What I mean, I misspoke. When the pKa is within plus or minus 1 pH unit. It's what it says up here. This is when they're most effective. In fact, let's do a problem here real quick. Let's use some acetic acid. Here's your equation for the weak dissociation of acetic acid. Here's the Ka. Right? And now I've put that in the context of the Henderson-Hasselbalch equation that I just derived for you. The pH is equal to the pKa plus the log of, this is A minus divided by HA concentration. Okay? And we're asked to calculate the pH of a buffer solution where both the acetic acid concentration and the acetate concentrations, that's the salt, that's what this is the acetate ion, when they're both equal to 2 times 10 to the minus second. And we're told what the Ka for acetic acid is. We're told that that is 1.8 times 10 to the minus fifth. Now for our Henderson-Hasselbalch equation, we need the pKa. So how do we get pKa from the Ka? The negative log. So pKa is equal to the negative log of 1.8 times 10 to the minus fifth. What is that equal to? 4.74. Okay, so that's the pKa. So we want to calculate the pH is equal to the pKa, which is 4.74, plus the log of the acetate ion concentration, which is 2 times 10 to the minus second, divided by the acid concentration, which is 2 times 10 to the minus second, what does that equal to? How'd you know that so fast? The log of 1 is 0. Okay? So you can plug this in your calculator, right? But the log of 1 is 0, so this term goes away. So this term goes away, and this is all equal to, the pH will be 4.74. Now, let's have some fun with this. Let's double the amount of acid that we put in here. Let's double the HA concentration. What are we going to get now? The pH is going to be equal to the pKa, which is 4.74, plus the log of, now the acetate ion is still the same. We haven't changed that. So that's going to be 2 times 10 to the minus second. But now we're doubling the HA, so that's going to be 4 times 10 to the minus second. What's that going to equal? And that's basically the log of 0.5 now, right? So 0.5, take the log of that. This is plus the log of 0.5, right? Which is what? negative 0.3. So that plus 4.74 gives us 4.33. So what did we do here? We added acid, right? We doubled the amount of acid. So we expect the pH is going to go lower because we're adding acid to the system, all right? But it didn't go a whole lot lower. It just lowered from 4.74 to 4.43. So it lowered a little bit, but not by much. That's what buffers do. They resist large changes in pH when we, in this case, we doubled it. We didn't just add a little bit, we doubled it. Okay? That's what buffers do. So now that we've gone through this example, I can go back and hopefully emphasize why it is that these buffers work best when they're plus or minus 1 pH unit from the pKa. Because here's the pKa, all right? We're looking for the change in the pH. Well, when these two are equal, all right, when A minus is equal to HA, we just showed that the log of 1 is 0, and so the pH is equal to the pKa. Once this becomes either 1/10 or 10 to the 1 or more, now the log of that will be greater than 1 or less than minus 1. Either way, now we're getting to be more than 1 pH unit away from what the pKa was. And it all has to do with how logs work. Logs are, in this case, log base 10. Okay? So we got to be more than a tenfold range different for it to have a significant effect on the ultimate pH. But it's all dependent on where the pKa starts from. And that's all dependent on what the acid is. Because pKa is directly related to the Ka up here. And we already talked about Kas and how those change depending on how weak or how strong an acid or a base is. So when you make a buffer system, you want to pick one that has a Ka or a pKa in this case that's close to the pH that you want to keep things stable at. If we want to keep our blood pH stable, all right, at a pH of 7.4, we want a weak acid that has a pKa of close to 7. Because that way, when we add a little bit of acid or add a little bit of base, all we're doing is tweaking this log function. And the log function won't change significantly until it gets to be greater than a factor of 10 difference between the HA and the A minus. So from a mathematical sense, that's how buffers work. So I instead want to get back to what you did yesterday in lab, okay? You did titrations of a strong acid and a weak acid. Here's the titration curve for a weak acid. And there are a couple of things that I'm hoping you found were different in them. Right? This slide right here gave away pretty much all the surprises in the lab yesterday. This is a titration curve of a strong acid, and here's a titration curve of a weak acid. And you can see there's a couple of differences. Now, one I hope that you noticed for sure was that the starting pH was different, all right? Because these were about the same concentration acid, so the starting pH is going to be lower for the strong acid because it dissociates 100%, whereas for the same concentration thereabouts, the weak acid won't dissociate as much. The other thing that I was hoping you would have noticed that at the equivalence point, as we've been discussing, what's left at the equivalence point, the spectator ions, what effect does that have on the pH? When you do a strong, the spectators are by definition going to be conjugates of negligible strength. So the sodium ion and the chloride ion have negligible effect on the pH, so when you get to this equivalence point, it should be pH 7. For the weak, all right, well, you've got a strong base, so the conjugate acid will be of negligible strength, but you have a weak acid, so the conjugate base will be a weak base. Right? That's the spectator ion. It's a weak base, so it should make the pH basic at the equivalence point. That's what's left over at the equivalence point. So you should have noticed that. The other thing that you might not have noticed was that the shape of the curve before you get to the equivalence point is very, very different. Because now you know this is a buffer and this is not a buffer. And we're adding pH to a buffered system. Here, you're adding hydroxide ion, it's not buffered. So you might have noticed that it stayed pretty much flat. I mean, I know it fluctuated a lot because those pH meters are crappy and they're only calibrated to pH 7. So when you get way out here, it's going to fluctuate. But when you draw your curve, it's pretty flat until you get to the big jump. All right? For a weak acid, it's not flat. It rises a little bit, and then it flattens out, and then it starts to rise again before you get to the big jump. That's because it's buffered here. Now, once you get to the equivalence point, it's no longer buffered. At the equivalence point, you've lost all the weak acid. It's been completely neutralized. So a similarity between these two, apart from the overall S shape of the curve, is that once you get past the equivalence point, it's exactly the same. It rises up and then it's flat. But let's explore a little deeper now this buffer action going on here in your weak acid. So this region here is buffered. Now I showed you a few other things in lab yesterday. We all know that here's the equivalence point, here's the volume that it takes to get to the equivalence point. And of course, you know how to take that volume and use it to calculate the concentration of the acid if you were asked to. All right, and then we talked about this. Now here on the slide it's called the midpoint. I also called this the half equivalence point. The half equivalence point, if you know what volume it takes to get to the equivalence point, well, we take half of that, 1/2 of that volume, and we get the half equivalence point. Now, if the equivalence point, that's where 100% of the HA, here, if I draw it this way, okay, H plus A minus, once we get to the equivalence point, all of this has dissociated. So if we started with initially, let's say, 5 molar, well, it doesn't have to be 5 molar. Here, let's move this over. If we had initially, let's say, 0.5 molar HA and nothing here, nothing here, then we don't need to build a rice table because here we're at the equivalence point. So we've neutralized all of the acid. That means at the equivalence point, there's no longer any acid here. It's all gone. And it's all gone into its components, in this case, in a 1-to-1 ratio. So if that's true at the equivalence point, then at the half equivalence point, well, if we had 0.5, then at the half equivalence point, we've dissociated half of it into its component ions. Right? You follow? And we can look at what the pH is, because this tells us what the hydrogen ion concentration is. So we can get pH from that. And this is the acid concentration, and this is the conjugate base. That's your HA and your A minus. So at the half equivalence point, the concentration of HA is equal to the concentration of A minus. And that's that log term in the Henderson-Hasselbalch equation. Let me remind you of that equation. Let's put it up on top here. pH is equal to pKa plus the log of A minus divided by the log of HA. If they're equal, this is where that log term goes to 0. So if I were to see what is this pH at the half equivalence point, That pH, by definition then, is the pKa. The pKa is the pH at the half equivalence point. And you can determine the half equivalence point from your titration curve because you know what volume it takes to get to the equivalence point. So I've got a few queued up here in your notes. We don't need to do these in order, and we don't need to do all of them. Certainly there's not time to do all the ones that I queued up in here. But since we just started talking about buffers, let's do this one here first. It looks like it's a little fuzzy, but I think you can see what you need to see in here. This is taken from the textbook. So the question is asking us what combination of weak acid and its conjugate base would be a good choice to produce a solution to use in a biochemical reaction that is optimal at pH 5. So there's a lot to unpack there, all right? We want to set up a buffer system that buffers our system close to a pH of 5. So this is our target. This is our target pH. And we need to come up with an acid conjugate base system that buffers very, very close to that target pH. So here's a list of different acids, and you're shown what the equilibrium is, if you can read that, and you're shown what the Ka is, and the pKa. So out of all this information, what do you want to look for to choose the right weak acid and conjugate base to make up a buffer system that will buffer close to pH 5? What are you looking for? Our equation, which is the Henderson-Hasselbalch equation, we want to look at the pKa because we know that this log function is less than 1 as long as we're within a 10-fold range of A- concentration to HA. And we know that at the pKa, we know from our curve that at the pKa those are equal. HA concentration is equal to A-. And we want to find an acid that has a pKa close to what we're interested in. So which acid do we want to use? What do you want to use? Acetic acid, right? Because it has a pKa of 4.75. Are there any others on here that we might consider using? Benzoic, maybe? With a pKa of 4.2? Or maybe even ascorbic acid? But acetic acid is the best because it has a pKa of 4.75. So we want our pH, we want the pH to be 5, ideally. Okay? And that's going to be equal to the pKa of acetic acid, which is 4.75, plus the log of A- over HA. Now, if we're using acetic acid here, if the concentration of A- was equal to the concentration of HA, what would the pH be? 4.75. Right? If these two are equal, the log of 1 is 0. It's this log term that mathematically explains why buffers do what buffers do. Because when we add acid or base, what we're doing is changing this ratio in the log term. That's the mass action expression. That's what happens with Q, all right, in Le Chatelier's principle. So until this gets to be 10-fold up or down, this number, the log of it, will always be 1 or less. And once you get above that, then it starts to change dramatically, as you can see on the titration curve. And what is the conjugate of acetic acid, by the way? Here's acetic acid, CH3COOH.
Acetate.
It's the acetate ion, CH3OO-. Now, you can't go to the stock room and buy a jar of acetate ions. Right? They've got to come in with a spectator. When you put it in solution, it will dissociate 100% to give us the acetate ion in solution. That's what we want. And the cation that comes along for the ride is exactly that. It's just coming along for the ride. It's a spectator. So you usually choose an acetate salt that is completely soluble in water under standard conditions. And if you remember back in Gen Chem 1, looking at like the solubility guidelines, that would be a group 1 metal, like sodium or lithium or potassium, okay? Those will be completely soluble. Typically when you do this, you use sodium. So we would put some sodium acetate in there. Looks like that. So we would want to have then, what ratio of acid and conjugate base would we need then for the log of that to be equal to 0.25? How might we figure that out? Do what? Antilog. That's right. If we take the antilog of this, 10 to the 0.25, 1.78. Okay, so that's your ratio. That means for every 1 mole of acid, we would need 1.78 moles of the conjugate, in this case sodium acetate. If we mix them in that ratio, then we should get a solution with a pH of 5, but that's buffered very, very close to it. So before you get too worried, okay, this is just for your information. I wouldn't test you on this. This is FYI. When you get into quantitative analysis or you get into the laboratory and you have to start doing this stuff, you would look this up in tables. There's tables published on what proportions do you mix an acid with its conjugate base to give you a buffered solution at particular pHs. But this is the math behind it, all right? So what I want you to get out of this slide, though, learning outcome-wise, is what's in blue, all right? Understanding how this equation works, understanding how buffers work, and being able to choose the right buffer to give us what we want. This is just, this is how you would actually do it if you had to. All right, let's practice again here. Let's do this one, a very similar problem. Here we're going to take, here's a table of weak bases, all right? And we're going to mix each base with the chloride salt of its conjugate acid in approximately equal molar ratios, blah, blah, blah. Produce a buffer with a pH of 9.2. So this question is asking for the ratio and whatnot. Let's not worry about that, all right? Let me change this. I don't care about the ratio anymore. I just want you to practice the overall idea, okay? What is the best weak base to produce a buffer for a solution at pH, what does it say? 9.2. What would you choose? You would agree? Who agrees? You fell for it again.
Fell for what?
No, what did you fall for?
It's a base, not an acid.
It's a base, not an acid. And this value here, actually, I didn't trap you, the textbook did, okay? This is the textbook's question. This is pKb that's listed here. It's not pKa. Okay, so you have to remember that relationship. Same idea, that where you fell into that same trap before when you thought you calculated the pH, but what you really calculated was the pOH. So we're going to need to subtract this from 14. But just remember, right, there's a couple of different relationships that we've been going over. They're all derived from the net ionic equation of an acid-base neutralization, right? It's all derived from this. Equilibrium, which is the K sub W. And remember, that's always equal to 10 to the minus 14th. Now, I say that's always equal to. That's under standard conditions, okay? The conditions aren't always going to be standard. When you have standard conditions, which is in this case 1 atmosphere pressure and 25 degrees Celsius, all right, it will be 10 to the minus 14th. But it's not always 10 to the minus 14th. If we have different temperature, for example, and you may recall back in chapter 14, Yeah, temperature is a major determinant of the rate constants, and that affects equilibrium and all that stuff. Don't worry, we're not going to get into that. Right? But if you're not at 25 degrees Celsius, the K sub W doesn't equal 10 to the minus 14. It'll be something else. But even if you're at a different temperature, this will still be true. Whatever the hydrogen ion concentration is, it's always going to be equal to the hydroxide ion concentration. That never changes, because that's how you get, that's the net ionic equation, right? And those will always combine to form H2O. So when we take a negative log transformation of all this, right, remember the pK sub W under standard conditions would be equal to 14. And if you look back on how we define Ka and Kb, and thereby pKa and pKb, I'll just remind you of these, right? Ka times Kb is equal to K sub W, which means that the pKa plus the pKb is equal to the pK sub W. I don't need to rederive all of these things for you, okay? It's all very circular. Now, unless you're told otherwise, we're going to assume that we're at standard conditions. So here our goal now is pKa close to 9.2. So which one is that going to be on this table?
You do 14 minus.
You do 14 minus, right. So 14 minus 9.2 is, what is that, 4.8? That's going to give me the pKb that's close to 4.8. Which is still the first one. It's ammonia. Does that make sense? Or did I just confuse everybody? It's just the same trap, again, as pH and pOH. Now it's just with Ka, pKa, and pKb. Just make sure you know what you're working with. And the big clue in here is that you're working with the base. And it even says with a weak base. All right, but when we talk about pH, that's always with respect to hydrogen ion concentration. And when we're talking about the Henderson-Hasselbalch equation, that's the pKa, not the pKb. So you just have to know what you're working with and know what the relationships are. All right, should we do more practice? Let's see. Oh yeah, actually, let's step back here. Because I want to also emphasize, again, this idea of being able to identify what is a buffer system, what makes a buffer and what doesn't make a buffer. We don't need to go through all of these. And in fact, in reviewing for today, I realized that the top part, also you need to understand how to convert the names into what the formulas are. So that's another skill. We don't need to spend time on that. Let's just use this bottom grid here to emphasize our ability to identify what's a buffer or what are the proper components of a buffer and what are not. So you have to look at what your equilibrium expressions are for weak acids or bases. And if you have the components of that, then you'll be able to make a good buffer system out of it. So let's look at the first one. Who doesn't know what to evaluate? All right. So how do you evaluate these? Look, these are all going to be in aqueous solutions. So they're ionic compounds, okay? Now, a lot of these are polyatomic ions that you might not have recognized before, but if you have a group 1 metal cation, it will be soluble in aqueous solution. And potassium, sodium, all right, those are group 1 metals. So that means, here we've got potassium and here's 2 potassiums. So that means we've got H2PO4 as the anion. What's the charge on that? It's negative what? Negative 1, negative 2? Negative 2? How many potassiums were there? What's the charge of potassium cation? Potassium cation is 1 plus. So this is 1 minus. Okay? And this one, 2 moles of potassium ions plus 1 mole of HPO4 2 minus. These are all part of the phosphoric acid series. So these are, you can consider this to be the acid and this to be the conjugate base of this acid. They are in fact part of a acid-base conjugate pair. How about this one? You do recognize HCO3 minus, hopefully. That's the bicarbonate ion. And you've got this, you know what that is. That's the carbonate ion. Right? And those are also part of a series, right? This is the bicarbonate ion. Remember that word, special word, amphoteric? Bicarbonate ion can act both as an acid and as a base. Here it is acting as an acid. All right, so yeah, these two form an acid conjugate pair system, so they would form a good buffer. All right, but C, having sodium bicarbonate alone, by itself, it's not a buffer. Okay, it needs to have a conjugate to come along with it.
Is the first one a buffer?
Yes, the first one is a buffer. So yes, yes, no. How about D? Yes or no, and why?
Yes.
Yes, and why?
That is. Can H2SO4 be amphoteric?
Can H2SO4 be esoteric? Amphoteric? What is H2SO4?
Strong acid.
It's a strong acid. It goes completely into H plus HSO4 minus. It has to be weak. Right? There's no equilibrium here. It goes completely. So even though HSO4 minus, which is right here, even though this is the conjugate base, it is. So this is an acid-base conjugate pair, but it's got to be of a weak. It can't be strong. If it's strong, it goes 100% to the products, and there is no measurable equilibrium that we can use to an advantage of a buffer. So this is no because it's a strong acid. It must be weak. Should I emphasize this more? It has to be weak, and it has to have the conjugate there for it to be an effective buffer at a specific pH.